This is the 26th video in a series that I'm making to support a course I'm teaching in elementary number theory. And this is the first video where we're looking at the idea of expressing positive integers as the sum of squares. And so the big question related to this is, when can we write a positive integer as the sum of two squares? So in other words, n equals a squared plus b squared, as the sum of three squares, or as the sum of four squares. And when we're talking about sums of squares, we take the parts to be non-negative integers, so we allow 0. So for instance, a perfect square can be considered as a sum of two squares, itself plus 0. Okay, so the first result that we'll prove is that the set of numbers that can be expressed as the sum of two squares is closed under multiplication. That is, if m and n can each be rewritten as the sum of two squares, so can m times n. Okay, so let's dive into this proof. So we're going to start by writing m as x squared plus y squared, and then we'll write n as z squared plus w squared. And here we're taking x, y, z, and w to be any non-negative integer. Really, we could just take any integer, but we might as well just take non-negative integers since we're squaring here. Now, there's a couple of ways to do this. I think in most elementary number theory books, you just kind of arrive at an expression for m times n, but I want to motivate how to create that expression. So let's take these right-hand sides and factor them over complex numbers. Actually, we're factoring them over the Gaussian integers. So let's write that. Over the Gaussian integers, in other words, z adjoin I, we can take m and rewrite it as x plus iy times x minus iy. If you multiply that out, you clearly get x squared plus y squared. And then similarly, we can take n and write it as z plus iw and z minus iw. Now let's look at m times n. And we'll commute the multiplication around in a way that's advantageous. So we can write this as x plus iy times z plus iw, and then times x minus iy times z minus iw, like that. Now let's multiply each of these kind of larger sets of parentheses out. So here we'll have x, z minus yw. That'll be the real part. And then plus I times xw plus yz. xw plus yz. Okay, so that's the first bit. Then we can do the same thing with the second bit. So we'll get xz minus yw. And then the imaginary part will be equal but with opposite sign. So we'll have minus I times xw plus yz. So that's what you get from multiplying this out right here. Okay, so now let's give these guys some names. Notice this thing right here is of the form a plus I times b. And this guy right here is of the form capital A minus I times b. But we've got a number and its complex conjugate. We know if we take that product, we'll get capital A squared plus capital B squared, where capital A is this thing right here and capital B is this thing right here. So in other words, we've taken our goal object and rewritten it as the sum of two squares. Okay, so now let's keep going. So after that starting proposition, we're going to work through a couple of lemmas that will allow us to prove a pretty big theorem. And that theorem will classify the numbers that can be expressed as the sum of two squares. So this first lemma we're going to look at says that if we have a prime of the form 4k plus 3, so in other words, this prime is 3 mod 4, then it cannot be written as the sum of two squares. Furthermore, if it divides a sum of two squares, then it divides each of the constituent parts. So if it divides x squared plus y squared, then p divides x and p divides y. We're actually going to start with this furthermore statement and use that to prove our main statement. So let's go ahead and suppose that p divides x squared plus y squared. But then in the language of congruence, that means that x squared plus y squared is congruent to 0 modulo p. Okay, but then that means that x squared is congruent to minus y squared mod p. And then from here, we can split this into two main cases. So the first case is that p divides x and p divides y. But that means this thing looks like 0 is congruent to 0 mod p. But also, this is exactly what we wanted to end up showing, so we would be done in that case. So now we want to look at the other case, which is p does not divide x and p does not divide y. Well, you might say there's a case when p divides x, but it does not divide y, but that clearly is not possible by this setup right here. But now we're going to be inspired by Fermat's little theorem to build this exponent of 2 up to an exponent of p minus 1. We can do that by raising both sides of this congruence to the p minus 1 over 2 power. So that's going to give us x to the p minus 1 over 2 times 2 is congruent to negative 1 to the p minus 1 over 2 times y to the p minus 1 over 2 times 2 mod p. But we chose that exponent for a reason, and that's because this is going to be equal to p minus 1. This is also going to be equal to p minus 1. But then by Fermat's little theorem, since p doesn't divide x and p doesn't divide y, that means this is going to turn into 1 mod p. And this over here is also going to turn into 1 mod p. So let's see what we've got. On the left-hand side, we have 1. And on the right-hand side, we have that is congruent to minus 1 to the p minus 1 over 2 mod p. All the rest of that stuff became 1. But if p is of the form 4k plus 3, that makes this exponent right here odd. Well, you can just check that. If you subtract 1, you get 4k plus 1. Divide that by 2, and you'll get that this is 2k plus 1. But if you take negative 1 and raise it to the 2k plus 1, you get negative 1. So let's see. That means that we have 1 is congruent to negative 1 mod p. But that's a problem. There's only a single prime where that happens, and that is the prime 2. But 2 is not of the form 4k plus 3. So that means we came to a contradiction in this case. Well, we didn't come to a contradiction in this case, so this must be okay. So that means we have proven that p divides x and p divides y. Now that we've got that taken care of, let's prove the main part of this lemma, which is that p is not the sum of two squares. So we'll start assuming by way of contradiction that p is the sum of two squares. So in other words, a squared plus b squared is equal to p. But notice that that means that p divides a squared plus b squared. But by the first thing that we proved, that means that p divides a and p divides b. But that means we can write a as m times p. We can write b as n times p. Now we'll throw that back into our original equation, and we'll see that we get p squared times m squared plus n squared is equal to p. Okay, but now we can divide off a p from both sides, and we'll see that we have p times m squared plus n squared is equal to 1. But that's clearly impossible because this over here is a multiple of p, but that's just 1. So we have a contradiction, but what did we contradict? We contradicted this ability to write p as the sum of two squares. Okay, so that means over here we have a partial answer to this first bit, and that is primes of the form 4k plus 3 cannot be written as sums of squares. Okay, so now let's move on to our next preparatory lemma. Okay, now we're ready for our next lemma. So just to reiterate, we just got done proving that if p is a prime which is congruent to 3 mod 4, it cannot be written as the sum of two squares. Well, let's suppose we've got two relatively prime numbers, x and y, and then p divides x squared plus y squared. Then p can be written as the sum of two squares. That's what we want to show. Before we jump into this, let's notice from what we just proved, p is not congruent to 3 mod 4, because if it were, then p would divide x and y, but that would mean p would divide the GCD of x and y. But that means p would divide 1, and that doesn't make any sense. Okay, so now let's jump into this proof. So let's suppose that m times p is the smallest multiple of p such that it can be rewritten as the sum of two squares. So in other words, m times p is equal to x squared plus y squared. Well, let's look at our assumption. We're assuming that these two are relatively prime and p divides the sum of their squares. But that means the sum of their squares is a multiple of p. Well, what we're doing is searching over all such situations of that form and picking out the one that includes the smallest multiple of that prime. So obviously what we're trying to get out here is that m is equal to 1. Because if m were equal to 1, then p could be written as the sum of two squares, but that's the goal of this lemma. Okay, so let's, by way of contradiction, suppose that m is bigger than 1 and see what goes wrong. So now what we'll do is take the residues of x and y mod p. But instead of taking them between 0 and p minus 1, we'll take them between minus p over 2 and p over 2. So just writing that out carefully, we'll take a over b between minus p over 2 and p over 2, such that we have x is congruent to a mod p and x is congruent to b mod p. So A and B are from a reduced residue system, maybe not the most standard reduced residue system mod p, but they're from the second most standard reduced residue system mod p, the one that's like symmetric about the origin. Okay, great. But now notice that tells us that a squared plus b squared is congruent to x squared plus y squared mod p, which is congruent to 0 mod p, from our assumption that p divides x squared plus y squared. Another thing which follows from this ordering right here is that 0 is less than a squared plus b squared, which is less than p squared over 4 plus p squared over 4, given that a and b are between negative p over 2 and p over 2. But that is equal to p over 2 times p. But let's hone in on what we've got. A squared plus b squared is a multiple of p, and it is less than or equal to, I should say, p over 2 times p. So it's the p over 2 multiple of p at most. But then the minimality of m says that m is the smallest such multiple of p that can be expressed as a sum of two squares. But that means that it has to be smaller than this multiple of p, which is at most the p over 2 multiple of p. Okay, so the long and the short of that means that m comes from the following set: 1, 2, 3, all the way up to p over 2. And obviously there's only one case when p over 2 is a natural number, and that's when we have an even prime. So you might want to think of that as like p minus 1 over 2 in most of the odd cases, but I won't write that. Okay, and now we're going to play this same game again, but working mod m instead of mod p. So let's take two numbers, and we'll call them c and d, and they're between minus m over 2 and m over 2. So they're from a reduced residue system mod m, not the most standard one, but the second most standard one, the one that's centered around the origin. And we want these guys to be congruent to x and y. I realize that should have been y mod m. So let's write that down. X is congruent to c mod m, and y is congruent to d mod m. Okay, so now we've got a bunch of stuff to summarize before we move on to the next step, and we'll do that at the top of the next board. Okay, we got a lot of moving parts on the last board. We have a minimal m such that x squared plus y squared is equal to mp. We argued that m must be less than or equal to p over 2. So it comes from the set 1 up to maybe like the floor of p over 2 if p is odd. Then next, we introduced some numbers a, b, c, and d. So a was congruent to x mod p, b was congruent to y mod p, c was congruent to x mod m, and d was congruent to y mod m. Now, let's notice that if we take c squared plus d squared, that's going to be congruent to x squared plus y squared modulo m from these two congruences, but that's congruent to 0 mod m, given that x squared plus y squared is a multiple of m from this thing up here. Okay, but that means that c squared plus d squared is a multiple of m. We'll say that it's m times n. And then we can get a certain size range on n the same way that we got this size range on m. So I'll let you guys work out those details, but it's pretty similar to what we did over there before. So we know that n comes from the set 1, 2, up to m over 2. Again, taking the floor if m is odd. Okay, great. Now we want to look at a pretty complicated object, but we'll see how it helps. We'll look at the number m squared times n times p. So let's notice that's the same thing as mn times mp. Now, mn is this product or sum of squares. It's c squared plus d squared. And then mp was this sum of squares, so it's x squared plus y squared. But then we know if we've got the product of two sums of squares, that's also a sum of squares. So in this case, it's cx plus dy quantity squared plus cy minus dx quantity squared. That follows from the proof of the proposition that we had at kind of the beginning of this video. But now we'll want to notice that c is congruent to x mod m, d is congruent to y mod m. So that means we can replace this c with x, this d with y, and this is congruent to x squared plus y squared mod m, but that's congruent to 0 mod m. So again, that's from these two things right here. And then likewise, c is x, d is y, so this is congruent to xy minus xy mod m, which is clearly 0 mod m. So each of these portions are congruent to 0 mod m. So that means that they are each multiples of m. So we might as well replace this with m times z. We could replace this with m times w. So let's see what that gives us. So that'll make this stuff collapse to m squared z squared plus m squared w squared. Well, we can reduce this by canceling an m from both sides, and we'll see that we have n times p is equal to z squared plus w squared. But let's recall that our n is most definitely less than m because it comes from this set. So this seems like a problem. Like, does this contradict the minimality of m, which we started off assuming? Well, if the GCD is 1, then yes, we have a contradiction. So if GCD of Z and W is 1, then we've reached a contradiction, which means that M was equal to 1, which is what we wanted to end up with. So that tells us that the GCD of Z and W must be equal to D, which is not equal to 1. Okay, so we'll sort that case out on the next board. Okay, we're about ready to finish this off. So again, M was minimal such that x squared plus y squared was equal to MP. In other words, it was the minimal multiple of P that could be expressed as the sum of two squares. But then we got another multiple of P that could be expressed as the sum of two squares, where this N was less than M. So the minimality was dependent on the GCD of x and y being 1. We saw that we have a contradiction if the GCD of Z and W is 1, so the GCD must not be 1. So let's set it equal to D. We can write Z as D times U, and we can write W as D times V, where the GCD of U and V is equal to 1. So that's a standard trick. Just divide the GCD out of each part. But now let's thrust these back into our equation. That leaves us with D squared times U squared plus V squared equals N times P. But notice the left-hand side of this is a multiple of D squared. That means the right-hand side must also be a multiple of D squared. So P is a prime, which means it cannot be a multiple of D squared given that D is not equal to 1. So that means N must be a multiple of D squared. That means N over D squared is a natural number. That means if we write this fraction, which is admittedly a little bit sloppy, we're still within the natural numbers. Okay, but now that means that we have U squared plus V squared is equal to N over D squared times P. So we've got another multiple of P, which is expressed as the sum of two squares. But notice that since N is less than M, N over D squared is also less than M. But that leads us to the same contradiction. We contradicted the minimality of M, but that contradicted an assumption we started with, was that M was bigger than 1. But that means that M must be equal to 1. So in other words, this prime can be expressed as the sum of two squares. Okay, so now we're ready to prove that the only primes that cannot be expressed as the sum of two squares are those of the form 4k plus 3. Now we're ready to prove that a prime P can be rewritten as the sum of two squares if and only if P is equal to 2 or P is congruent to 1 mod 4. So the forward direction is essentially what we proved before, but just via the contrapositive. So let's prove this reverse direction. Well, let's start with our simple case first, which is the case when P equals 2, which equals 1 squared plus 1 squared. So we're good to go in that case. So now let's jump into the other case. Let's suppose that P is congruent to 1 mod 4. But let's recall in this case that -1 is a quadratic residue mod P. So if you remember correctly, -1 is a quadratic residue mod an odd prime P if and only if that odd prime is congruent to 1 mod 4. But that's what we've got here. And I've indicated that with this Legendre symbol, -1 by P. Okay, but that means that there exists some integer which I'll call x, such that x squared is congruent to -1 mod P. Well, just remember that being a quadratic residue means that you have a solution to this type of quadratic congruence. But by the definition of congruence, that means P divides x squared plus 1. And let's notice real quick that the GCD of x with 1 is obviously equal to 1. But now we can apply our previous lemma to say that p is equal to a squared plus b squared. Remember, if p divides a sum of squares that are made up of relatively prime parts, then that prime itself is a sum of squares. But that's exactly what we wanted to end up with. Okay, so that finishes the proof of this theorem. So now let's move on to our main result. Now we're ready for our main result, which classifies all natural numbers that can be written as the sum of two squares. So in fact, n can be expressed as the sum of two squares if and only if every prime of the form 4k plus 3, so every prime that's congruent to 3 mod 4 that divides n, occurs with an even exponent in the factorization of n. Okay, so let's maybe do this reverse direction. So let's suppose that we have a prime factorization. So we'll take n and we'll write it as 2 to the a, p1 to the r1, all the way up to pk to the rk, and then q1 to the 2s1, ql to the 2sl. So with my notation here, I have all of the pi are congruent to 1 mod 4. That means they can all be rewritten as the sum of two squares. So this can be rewritten as xi squared plus yi squared equals pi. That's what we just got done proving. And then all of the qj are congruent to 3 mod 4. But notice those are all occurring with an even exponent. So that means that they are all already perfect squares. And furthermore, 2 can be written as a sum of two squares as 1 squared plus 1 squared. So now we've got n is equal to 1 squared plus 1 squared to the a, and then x1 squared plus y1 squared to the r1, all the way up to xk squared plus yk squared to the rk. And then as we noted, all of this has an even exponent already. So this itself is a perfect square. We could just call that as a squared. But the very first proposition we proved in this video was that the set of numbers written as the sum of two squares was closed under multiplication. But here we're just taking a finite product of things written as the sum of two squares. If you're worried about this, you could just write it as a squared plus b 0 squared, but that's really no worry. So in the end, we can rewrite this as c squared plus d squared by iteratively applying all of the results from previously in the video. And for the forward direction, I'll leave that as an exercise. Now, before we finish this video, I want to prove something about the uniqueness of writing primes as the sum of two squares. Let's finish this video off with one last result, and that is if a prime can be expressed as the sum of two squares, then that expression is unique. So we'll start with the p equals 2 case, which is 1 squared plus 1 squared. Well, that's clearly the unique expression of writing 2 as the sum of two squares. Notice if we do not have 1 as one of the parts, then it's going to be bigger than 2. So that means the only interesting case here is p is an odd prime. Well, now we just got done proving that only primes of the form 1 mod 4 can be rewritten as the sum of two squares. So that means that p, in fact, is 1 modulo 4. Okay, well now let's assume that p can be rewritten as a squared plus b squared and can be rewritten as c squared plus d squared. And we want to show that these expressions have to be the same. Well, let's notice that p is odd. That means that a and b have opposite parities, and c and d also have opposite parities. Notice if they had the same parity, that would make p even, but we already have an odd prime here. Okay, so we might as well say that a and c are both even and b and d are both odd. So let's do that. A and c are even, b and d are odd numbers. Okay, But now taking p equals p and moving things around, we see that a squared minus c squared is equal to b squared minus d squared, like that. Another thing we can note is that a and c are both even, which means a squared and c squared are both multiples of 4. So that means both sides of this equation are multiples of 4. In other words, it's 0 mod 4. But that also means that we can divide both sides of this equation by 4, and we're still within the natural numbers. So let's do that. So that tells us we have a minus c times a plus b over 4. I'll go ahead and factor this as a difference of squares while we're at it. B minus d times b plus d over 4. So we've got that new equation. And now next, we'll take the GCD of a minus c and b minus d and set it equal to the number x. So those guys must have a GCD, so we'll just set that GCD equal to x. And so that tells us that a minus c over 2 is a multiple of x. We could call it x times y. And b minus d over 2 is also a multiple of x. We could call that x times z. And then by construction, the GCD of y with z is equal to 1. But now plugging this expression up here, we'll see that we have x on both sides of the equation, which we can cancel, leaving us with y times a plus c over 2 equals z times b plus d over 2. Okay. Then given the fact that y and z are relatively prime, that means a plus c over 2 must be a multiple of z, and b plus d over 2 must be a multiple of y. So let's write that down. We've got a plus c over 2 is a multiple of z. I'll write it as z times w. Okay, but that means that this left-hand side is equal to z times y times w. This right-hand side must also be that, so we know that exactly what the multiple of y b plus d over 2 is. B plus d over 2 is y times w. Okay, so we're about to land at a contradiction, but we don't have enough room to show that. On the last board, we ended up with the following equations. A couple steps before that, we had these equations. And it doesn't really matter how we constructed x, y, z, and w. At this point, we can just use them as is. Okay, so now we'll take these equations and solve for a and b in terms of x, y, z, and w. We could also solve for c and d, but we don't need that as much. So doing that, we'll get a is equal to xy plus zw. And then we'll get b is equal to yw minus xz. And now let's throw that into our expression for p as a squared plus b squared. So we have p is equal to xy plus zw quantity squared plus yw minus xz quantity squared. Okay, but that should look familiar from one of our first propositions where we took the product of two sums of squares and got a new sum of squares. And that should give you the motivation that this factors like x squared plus w squared times y squared plus z squared. Which may not seem like a problem, but notice what we've done is we have just factored a prime, which is clearly impossible. That goes against the definition of a prime number. So we've come to a contradiction. And what is that contradiction? Well, that would be this assumption that we can indeed write this as two different sums of squares. Okay, so let's finish this video off with a couple of warm-up problems. So here are a couple of nice warm-up problems. So let's write the following four integers as sums of squares, if possible. So 99, 45, 80, and 490. Just for a little bit of a hint of how to streamline this process, let's notice that if we take 65, that's 5 times 13. Those are both 1 mod 4. So we've got nothing of the form 3 mod 4 in the factorization, so we don't need to worry about that at all. Well, notice that 5 can be rewritten as 1 squared plus 2 squared, and 13 is 9 squared plus 2 squared. But then that formula from that proof of our first proposition tells you how to combine these two objects to give you an expression for 65 as the sum of two squares. So I think in principle, if your numbers are quite large, it's better to break it up into its constituent parts, write parts of that as sums of squares, and then combine them together with that equation, rather than just trying to like brainstorm and finding 65 in this case is the sum of two squares. Although 65 is pretty small, so it probably wouldn't be that bad. Okay, that's a good place to stop.